sine Q dVO plus okay, for this single equation, how many parameters we have? We have flight path angle, that is the first parameters. We have the flight range angle, so that is the second parameters, and also we have Q. So in total, we have three parameters here in the single equations. So usually, this equation will be a little bit confusing in solving. And based upon the given situations, and from here you can see if we like to solve using this equation to solve for something, at least we need to know two of the parameters and then solve for the other one. Otherwise, the things won't be feasible because then we have a lot of situations here, there. So here it comes to the situations. We're going to analyze for this equation for the situation is Q less than 1 and Q equal to 1 and Q greater than 1. We want to study the situations, the solution process for the three situations here. So here, the textbook provides us the very schematic, very brief discussions about those kind of the possibilities, and it's not easy to follow up in terms of the writings. So here I try to use examples using certain numbers to explain the situation here. Okay, so for case 1, when QBO is less than 1, and we see what happens. So for example here, say Q equal to QBO equal to 0.8. Okay, and then we want to know what is the possible range for psi and what is the possible range for phi BO. Okay, so here we only give these situations. We want to develop the possible solution range for okay, so that is this information we look for. And with the QBO implemented, so therefore 2 minus QBO and QBO, this one is 1.2 and 0.8, so that is right, 1.5. Okay, so therefore here we can rewrite that equation sine Q phi BO plus V over Q equal to 1.5 times sine. Okay, so right now the equation is simplified into, I simply plug into there to get to here. So for these equations, and we want to solve for the possible range. So now you can see, by confining to the sine functions, any sine function, its maximum possible value will be equal to 1. So here we can say one value. This value must be always greater than the whole things here. So from these things, you can see by comparing this term and this term, we know that 1.5 times sine phi over 2 must be less than equal to 1. It cannot be arbitrary. So from these observations, we would know the range of the sine. Okay, and what is that one? That one, again, this is the Earth's surface. This is the center here, and this is the burnout point. So that is the free flight range. And this is the re-entry. So basically, this angle is defined by we call the flight range angle. Okay, so right now we're looking for this one. And so for under these situations, we know this side cannot be arbitrary. It do have certain value here, so we can see we solve for this one. So that means sine phi over 2 is less than or equal to 1 divided by 1.5. So that means under these situations, we're looking to the trigonometries here. So these are sine functions. Right now we know a function, this is a theta and this is sine theta. So for any value that is less than, say, this value is 1.1 by 1.5, I think that one is how much? 2/3. Okay. So if we are given the value 2/3 and we asking this one is less than, so here you can see using this information, this is our solution range. Can you see? You punch your calculators again, that will only give you this range. This one you need to do it manually. Okay, so for this value here we have is this value corresponding is theta equal to 1.4595, and this is the radian. Okay, so this is the first value theta 1, and this one basically is 2 pi minus theta 1. Okay. So therefore, by observing this, so therefore, the first value equal to, so therefore the first value, the V must be I make okay, let me take this one. Okay. So, and also on the other side, the V over 2 is greater than pi minus theta 1. So from this one, we'll leave it for this moment. This is radian. Okay. So from here, we have the two informations. Let me think is the better way is this. So right now we have the ranges like this, and so from here say we define it. So that is the general solution process. And now if we want to define the maximum range condition, that is happen when sine and 2VB plus V over 2. And that one, again, we follow up our problem here. For the maximum situation is this, when the situation of this value equal to 1. Okay, so that is the definition for this one. So under these situations, then we can see corresponding to that one is when phi equal to phi maximum under this situation. So therefore here we can, using the two forms, then that means 1 equal to 1.5 times sine phi over 2, and that situation is when the value of the psi equal to maximum. So from here we can see the psi maximum is, we can take that value is 1.46 radian. Okay, so in these situations, basically here for the maximum here, we kind of the thinking is in this range. And so once we determine this step, then the final one, the next step is to solve for VBO. And for the VBO, and again, our situations is we have the things is sine. Again, we follow up from this description here, the BO plus the phi over 2. And again, it is in general it's less than or equal to 1. And when equal to 1 is equal to 1 under the maximum conditions, so that is the maximum. Okay, so the one equality will happen only this value equal to this. Okay, so for this case we can see, and so we see, so we can split it into the two situations here. So that is what is the best way? Okay, so we can, so okay, so that is, let me see. So condition 1, when it is equal to 1 under this case, and condition 2, so sine 2 VBO plus phi over 2, when the other condition is less than 1. So right now, basically, two conditions basically cover the whole possible situation for this one. So then for this case, we see what happens. So this one is equal these situations, basically this one, let me add it up this, because again this equation is always satisfied. So let me plug in that number here. So this one is equal to 1.5 times sine phi over 2. And now for the second situation we study is the last one. So this is less than 1. So this situation is when happened is this range, this number fit into this range. Okay. So when this situation happens, we know the right hand side is less than this one. So let me define this as the beta, whatever the value beta here. For if we are given any value of psi, then we can always calculate this number, and I call that number as beta. I'm going to solve for VBO. So therefore, with this number introduced, the VBO basically is equal to, again, let me draw the curve here. This is psi value to VBO plus psi over 2. And then this is the angle here, so that is the sine functions. And right now we are looking for any value of the beta. Beta is less than 1. So the beta value is anywhere under the peak value here. So here we, again, you can see we have two possible value here. And then we call the value, say is the beta 1. This value is equal to beta 2. So under this, no. This one value is arc sine beta, and this value equal to pi minus arc sine beta, right? Okay, so now we can see, therefore, corresponding to this value, 2VB plus psi over 2 equal to sine minus beta. Okay, so basically sine minus beta, let me plug in that number here, so that is the arc sine. And in general, 1.5, and 1.5 is this one. So let me put into the formulation. So that is Q minus QBO divided by QBO times sine and phi over 2. You good? So therefore, for solving this one, the phi BO is equal to 1/2 of arc sine, Q minus QBO, and QBO, and sine and phi over 2. And then minus this one. Okay, so that is the first numbers here. Then the second numbers corresponding to this value basically is pi minus this one. So basically the answer is, we can convert it into here, arc sine. Okay. So right now using this example here, and we have the number constant, and then we can discretize the whole situation into the individual conditions. So right now we have two possible values. So phi BO is equal to this or equal to this value here. Okay, so the two situations is when what happened when for the situation the psi equal to less than the maximum value here. Okay, so here we have so many possible situations, and let me explain a little bit more about what that means. So if this is the Earth's surface, and this is the center here, and so if this is a burnout point, and here we have a free flight. So from here, for example, say right now we're looking at these situations. These situations is for these conditions. So for these conditions, say if we are given the Q, okay, so for example, for this case, it's 0.8. And do you remember what is the definition of the Q? Basically, the Q is by definition, is the RBO, VBO squared. Q is determined by the positions, the RBO, and also the velocity at the burnout. So at that moment, if say we determine the burnout positions, and from the rocket, when we turn it off, we know the velocity, you still have the option, you can tune the flight path angle, either this angle, or this angle, or this angle. You have an option to do it, okay? And the different angles will bring the rocket in the free flight to different range. If you shoot very high, here is compared to this is local horizon. Okay, so compared to the local horizons, and this is the flight path angle is defined by this, if this is the V. Okay, so this is the flight path angle. And so for this case, we call the high flight path angle. This is called the low flight path angles. If you shoot high, basically here you can see that shooting into the sky and it will coming down. In this way, that corresponding flight range will be shorter. If you choose the flight path angle in the smaller one, basically, hopefully you can have the information you can shoot for longer. So basically this one, if you can imagine, right now you're holding a garden hose. So that will be the very good imagination, and to resemble this situation. For example, if you imagine you hold a garden hose, and at the outlet of the hose, and that's the water, and that with the speed, and basically that determined is by the hose size and the pressures from the faucet there. So if you choose, say, if we are given the outlet and the water outlet velocity and pressure is the same, then basically if you change in the hose angle, you can feel the path of the water, right? And if that you tune the angle very high, basically 90 degrees, then basically you have the water shooting high and then coming down to your head. If you hold it at 45 degrees, based upon the physics, then 45 degrees can give us the maximum range. And say 60 degrees and then or 30 something degrees, that the two different values would give us the same destinations. So using this one as one example, that can be the very good, but not very exact representation of these situations. So now we're looking for these situations here. So first one, we know we have the maximum range we can achieve. So given any value of the Q, that has determined the maximum flight range you can shoot for. So here is a free flight. So this is re-entry here. So whatever the Q given, that is a maximum. Wherever we are given this Q, this value has been determined. If you want to go further beyond this point, unless you change the value of the Q, otherwise once Q is determined, this is determined. So you can only play around the parameters such that you can shoot in the range, say anywhere in between this range. So for example, if you want to go for the maximum range, we have the value corresponding to here. So for the maximum here, we have a maximum value. Then in this way, you can determine the VBO. So in this situation, hopefully you can add it up here. So basically, under the maximum situations here, the VBO corresponding to the maximum situation is simply equal to how much? This is 1, so that is pi over 2 minus psi over 2 divided by 2. So this is the corresponding flight path angle corresponding to this value, because I simply solve for these equations. I take arc sine of 1, that is pi over 2. Pi over 2 minus v, and then divided by 2 is this one. So again, if we want to achieve the maximum psi, then the VBO we must use in that angle we calculated. Okay. On the other side, just like this time the North Korean, they fly shooting the launching, and they didn't choose go to maximum, because the maximum, I believe that rocket will allow them to go to maybe United States. They didn't do it, but they choosing the option is this. They choosing is these options. For this option, they choosing is the maximum range is less than the flight range less than maximum. So for example, their choice is, say, for example, is only let me do this one here. So again, this is the Earth's surface, and this is the burnout, and these are local horizon. And right now, for these situations, they only fly to here. So basically, these situations is something like this one. You see? Okay, so under this situation, they very likely they choosing parameters. Either they choose this angle, or they choose this angle, and then they can do the things. And so here we can try to do it. So for this case, for 0.5, and for these situations, because this is the parametric expressions based upon the different value of the size. So as long as psi is less than the maximum, we always have two solutions, and then we can plot it to see what happened. So we given the psi and the range, and say for psi equal to from 0 to this maximum value, and then we see for the first value, then that will be something like this. We use the MATLAB to curve to draw. and this is the for this value here. And for this value, again, we can also draw it. So that value is schematically is something like this. So corresponding, this is corresponding is the maximum value here. So anything, if we have, say, let me using the solid line. So for anything, if we want to have, they say, decide, say for this launch, we only want to take this as our value, then we have the two options to choose our the fee. So that means either at this point you shoot high or shoot very low. So that is the two possible the V, and that can bring you to this range. Okay, so this time for the North Korean, I think they're using it under these situations here. Okay. So so under these situations, maybe we can look at one real example here. So for these situations, and say the international intercontinental ballistic missile, okay, and it has the total flight range and 4,700 nautical mile, and then here we have the the power flight range, and that is 45. And this is the range. The range is 155. And the burnout occurred at an altitude 150 mi, and then with QBO equal to 0.8. Okay, so now we want to know is want to determine the time of free flight. And time of free flight, basically here the solution is this. The first one from our previous, I think chapter 4, Kepler's equations, the time of flight, and this is the meaning the free flight, okay? That is for notations. And this is the time of flight from our earlier, the chapter 4. We have these equations. And then I will give you explanations what is those symbols. So probably that we can have a new section here.
Okay.